two categories, what may be called not a gas or a non-gas and a gas. And within gas, we have the most idealized situation, which we call the ideal gas, and then a real gas that deviates from this thing. This is the easiest thing to work with in thermodynamics, for the equation of state is very simple, and that is the central idea of all this discussion on properties of a substance as to how can I get all the properties for a given state if I have one, two, or if there are minimum two independent properties are specified. Then we went through a discussion about how a material behaves, and we took the example of water at ambient conditions and looked at what happens to it when you do isobaric heating. And there we came across that substance can exist in many phases. We said that there is a compressed liquid, which can also be called as a subcooled liquid. Then we came across a saturated liquid, saturated vapor, and superheated vapor. And then something which is beyond this, we call it the supercritical fluid or the dense fluid. So we learned that substance can exist in so many states, beginning from ideal gas, which is one extreme, to real gas, superheated vapor, saturated liquid, compressed liquid, and if you go below temperatures below that, then you will have the solid phase. Then we came across something which said that this and this, the saturated liquid and saturated vapor, can coexist as a mixture, as a phase mixture in equilibrium. So any mass fraction of liquid and vapor, if it is corresponding to the saturated state, it will be there in equilibrium. Then we said that in saturated state, pressure has a one-to-one correspondence with temperature and vice versa, which implies that these two are not independent properties, but basically they are only one property. And to completely specify the state, we need some more information. That information can come either from data on S or H or V or U. But we introduced one more parameter that will complete this definition of the state, which we called X, the dryness fraction or the quality. And the way we defined X is that X is equal to the mixture volume divided by the total mass of the substance in that. What we mean by this, we can call it say V total upon M total meter cube per kg. We took one example yesterday and we said that look, I have a vessel, there is so much liquid sitting here, the upper space is filled with vapor. Then what is the dryness fraction? And for that we define the system boundary as this one, and this is the dryness fraction we are now defining for this. It's not necessary that this is the only way in which a liquid and a vapor in a saturated state can exist with one another. Another example is a tube which is being heated, like the evaporator of a refrigerator or evaporator of an air conditioner. And at the entry of this, we say we put saturated liquid. Dryness fraction is 0. And we ask that the liquid was completely occupying the space inside the tube. What happens to this liquid as it gets heated and it flows through? So as some heat is added, it forms small vapor bubbles which are largely floating in saturated liquid. As more heat is given, these bubbles become bigger and they still the liquid around this. And even more heating takes place, these bubbles start to occupy a larger space in the tube, and the liquid is now in smaller amounts in a very irregular fashion. And then we could have a state where there is lots of vapor, small amounts of liquid as fine droplets, and finally only vapor. So physically this is what happens in the tube. But we can always pick up a state at that point and say what is the dryness fraction here or what is the dryness fraction here. So you could have dispersion of vapor bubbles inside a large liquid, or in the other extreme, fine droplets moving around in vapor. This is also what happens in steam turbines where it's operating in the wet state. And in between, it's very irregular behavior, and we cannot really write equations and solve out and say what is the answer. But qualitatively, we can say that if I take a element here, what is the dryness fraction? And we know that as this heating takes place, x goes from 0 to x equal to 1, and then if more heating takes place, the temperature rises, and it is then a superheated vapor. So these are different ways in which one can encounter this thing, which is a mixture of a liquid and a vapor in a saturated state. In all cases, the definition relates to the definition as per the system is concerned. This is the system here. This whole thing is the system over there. And this is what we write. And we can then write that this total volume is volume occupied by the liquid, the F, plus volume occupied by the gas, the vapor, divided by the total mass. The total mass is mass of the vapor, mass of the liquid, plus mass of the vapor. The volume itself we can write in terms of specific properties. This is mf into Vf, which is a specific volume of the vapor. So that is the volume occupied by the vapor. And similarly, the liquid, mass of the vapor multiplied by the specific volume of the vapor. This is the volume occupied by the liquid, this is G, vapor, divided by the total mass. And then we can break this up, that this is mass of the fluid, which is the liquid, divided by total mass, multiplied by specific volume of the liquid, plus mass of the vapor, divided by total mass of the mixture, multiplied by specific volume of the vapor. And here we define this property, that this ratio, mass of vapor divided by the total mass, this is our dryness fraction. This is V. This is X. This is a specific volume of the mixture. That is what we are trying to calculate. So this is equal to, this becomes 1 minus X times Vf plus X Vg. So the specific volume of this mixture or this mixture or this mixture can be calculated by a relation where we know the dryness fraction, we know specific volumes of the two phases. So although this equation looks like we have three variables on the right side, we have X coming here and these two coming here. But since these correspond to a saturated state, they are basically only one variable, which means that either we know the pressure or we know the temperature, and then from the property tables we can go and pick up Vf and Vg. So we are basically looking at only one variable here and one variable over there. That's what we need. We need two things, and that's what we can get from here. We can recast this equation and write x is equal to, and if we do that, we get the answer that x is equal to V minus Vg, Vf, upon Vg minus Vf. That's how we can calculate it. And what it tells is that if V is equal to Vf, that means the entire volume is occupied by the saturated liquid state, then x is equal to 0. And if V is equal to Vg, that means there is only saturated vapor, then x is equal to, and in all applications, x will take a value between these two, and this and all these are defined only if we have a saturated state. So if say that we have in a vessel or any system, we only have a liquid. If it is saturated liquid, its dryness fraction is 0. But if it is subcooled liquid, then its dryness fraction is not defined. Okay, so subcooled liquid is not a saturated state, so x is not defined. And similarly, the other extreme, that if you have only vapor in this, if it is saturated vapor, then yes, x is equal to 1. But if this is superheated vapor, then x is not defined. Sometimes somebody will write x is equal to 1, even though it is a superheated state. That's wrong. And same thing, if subcooled liquid is there, one says, no, there is only liquid there. Since only liquid is there, so x is equal to 0. That's incorrect, because state is subcooled, and for that, dryness fraction is not defined. What we had also mentioned is that we got this property relation for in terms of specific volume, but the same thing also applies for all the other properties. So if you want to know that for this mixture, what is the specific enthalpy of this mixture, we can say that H is equal to 1 minus X times HF plus X times Hg. And we said, what is the, ask the question, what is the specific entropy of this system? Then S is equal to 1 minus X SF plus X Hg. And the same thing we can use for U. U is equal to 1 minus X UF plus X UG. So how do we get values of UF and UG? We discussed that a little bit yesterday, and what we have is tables and then computer programs also to help us with that. To give an example from the tables, the table heading will be saturated state, and in this table the first column could be either pressure, or in some cases it could be the temperature. If the pressure is given, then after that follows a temperature column, which is the saturation temperature at this pressure, Tsat at this P. If the temperature is the first entry, then the second column will be Psat at that temperature. So we'll have an entry here, an entry here, like this. And after that you will find that there is an entry for Vf, Vg, then Uf, Ug, Hf, Hg, SF, and S. So all one needs to do is pick up where the pressure or temperature is, and you get all the saturation state properties coming out of there. So that's how we use these tables. In between, if these are discrete values, one has to do interpolation. Alternately, you can use either software packages or you can go online, and there are online things where you say, they ask input two independent properties. And when you input those two properties, and they will give options. You want to input pressure and temperature, or pressure and dryness fraction, or pressure and specific enthalpy. And you pick that option, put those two values, it will tell you all the other properties that we are talking of over here. So everything comes up. One can also write these equations and integrate it with a program that then people do it when you are doing complete analysis of thermodynamic systems. You want to frequently call properties and you need that, so you write a small subroutine. And there is one more definition that comes in, and that has to do with the fact that we define a new term, VFG, as VG minus VF. That means the specific volume change during the phase change. And similarly, we can define UFG, HFG, and SFG. So I'll just write down one of these. This is HG minus HF. And this is called specific enthalpy of evaporation. And its value at 1 bar for water is what you have learned in school. You have 540 calories per gram, or the equivalent in joules per kilogram. So if you want to express the value of X, say V, you can write that VF plus X VFG. That's another way of writing the same equation. Or in the earlier equation that we wrote, where we defined dryness fraction in this way, this we can further write as V minus VF upon VFG. In many cases, the tables will give values of these also, but there are many cases where they may not give these values. And the reason would be that if you want that, we can just calculate it from the values of HF and HG. That's what is there. And in the tables, this property relation also is always true. H is equal to U plus PV, the property relation we have already seen. So in some cases, even U may not be given, only H would be given, because in many engineering applications, H is what is used very frequently. So you will find that there is no properties for U given. No need to panic. We know that H is given, P and V are given. From there we can calculate it. So let's now look at some property diagrams. We also saw yesterday something that we have plotted, that how does this whole thing depend on the pressure at which this behavior is seen, and we came across two different set of lines. We were making temperature on this axis and specific volume on this side, and we came out saying that there is a line which is like this, where each point represents x equal to 0. This is the saturated liquid line. And then we said that there is the other part of this line which goes there, where points on this, they represent dry saturated vapor. And we define one thing, which is this point here, as a point where the differentiation between vapor and liquid phase disappears, and all we are left with is one state. This is called the critical state. And all properties at the critical state for a given substance are unique. They are just listed out separately. And last time we looked at the fact that if we started with 1 bar, what happens, and we made a picture of something like this. Then as the pressure kept increasing, we said that this goes up, and we start seeing lines over there. And similarly, further increase in pressure, this side is there, and all the states fall over there. In the critical state, there is a point of inflection here, and then it continues. And at pressures greater than the critical pressure, we do not see any phase change. This is what is called the supercritical fluid. and all states in this region where above the critical pressure and above the critical temperature, they are called supercritical states. So we looked at this TV diagram, and now let's look at the TV diagram for some other substances. Okay, so let's look at this picture first. I have plotted what I have explained by freehand over there. These are real numbers for a substance which is a refrigerant R134A. This is a common refrigerant which you now see in refrigerators and some air conditioners. On the y-axis is temperature in degrees Celsius. The x-axis is specific volume in meter cube per kg. These are real numbers. Now what you see is that this line here going all the way up, this is the saturated liquid states. And they are all pretty much like a vertical line telling us that the specific volume change with temperature is quite negligible. But when we go to the saturated vapor state, we see this line coming here. And you can see a very large change in the specific volume, something which was like 0.001 or 0.002 of that order has now become at least 100 times bigger. It's now 1 over here and goes up to 2. So the first thing to note is that in many of the cases, there's a very large change in specific volume that accompanies this phase change process. Water at ambient conditions, when it changes phase from liquid to vapor, its specific volume increases by almost 1,000 times. So there's a huge increase in volume that takes place. But when we plot this thing in a different scale, we just change the y-axis, the x-axis to a logarithmic scale. Now you begin to see a curve which looks something like what I have been drawing. So on this side, this is the critical point at the top. The parameters are the same, temperature in degrees Celsius, specific volume in meter cube per kg. And on this side, we see that there is a very steep line, which is the saturated liquid states. And this side, we have the saturated vapor states. So this begins to look like the picture that we have been making. And yesterday we saw that on this side, all those lines where the pressure dependence is so weak that almost all states in the compressed liquid state, they all are pretty much close to this line itself. It's not falling on the same line. So that's one thing we get to know, that pressure does not have a very big effect on specific volume, and later on also, as we will see, it doesn't have a very strong effect on specific enthalpy or specific internal energy also. Okay, so this is a real behavior and what we have been looking at. And now let's see the same thing for different substances. Yeah, okay. So what I've tried to do here is make a similar TV diagram for different substances. We can do that because temperature scale is absolute. It is the same temperature scale everywhere. And the specific volume is also an absolute scale. So that is meter cube per kg here. Okay, there is a small change here. I've written here temperature in degrees Celsius. This is not right. This is temperature in Kelvin. Okay, so we can make that change here. This curve at the top is for water. The bottommost curve here, this is for nitrogen. So you can see that it is going to very, very low temperatures there. Something like 126 Kelvin is the critical point, the critical temperature for nitrogen. And in between here, there are two things I have drawn. One is propane, which is this curve, and just next to that is this curve, which is for R12 CCl2F2, which is a refrigerant. And we can see the range over which these properties varies. Nitrogen goes everything below 126 Kelvin, oxygen will go below that, hydrogen will be even smaller than that. So they will all be like small domes over there. In between we get a lot of substances. Water comes here, and all of them have the same behavior, a very weak dependence on pressure on the saturated liquid side and fairly strong dependence on the saturated vapor side. But they all have the same general thing that I have been describing. So that's the important thing about this. So we made a separate plot last time where we put on the x-axis the temperature and on the y-axis we plotted the pressure. And the lines that you see on this picture, these are lines of saturated states. So if this is the temperature, the question is what is the saturation pressure at that point? If this is the temperature, what is the saturation pressure here? And all these lines are for different substances. On the extreme left is hydrogen. So we can see that the topmost point is the critical point for each of these substances. So hydrogen goes to very high pressure, but the critical temperature is like 10 or 20 Kelvin, somewhere about that. Then you have nitrogen, which is there and goes up to about 126 Kelvin. Then you start getting here like carbon dioxide, and then a lot of curves which are very, very similar to one another. They are R22, R134A, these are hydrofluorocarbons of different types. And then this one, which is butane. The reason for bringing butane and all these substances together is that if you look at the thermodynamic properties of all these, they are somewhat comparable. And so one would say that I could have used butane as a refrigerant, or better still, substitute that hydrogen in butane or propane or ethane by chlorine or fluorine, and you start getting all these wonderful chemicals which were the refrigerants. And it was these wonderful chemicals that were responsible for ozone layer depletion. And so this refrigerant R12 I have not put here, but R22 is a little bit still in use, but it is slated to be banned, and we are moving out to R134 and other refrigerants where chlorine is much less or if not there at all. So there was a huge environmental problem with these materials, and so while they are very popular for a very long time, starting about 20 years back, the global community decided that we don't want this, they are too bad for the environment, we should go for more eco-friendly refrigerants. That's what you see happening today in ACs and refrigerators. Then you have this state here, this line is for water. And to tell you that it's not just water and all these substances which behave like this, we have gone a little bit further ahead, and here these are the properties of mercury. We have seen mercury in the lab, which is a liquid. What it means is that at that 1 bar pressure, mercury has a saturation pressure, there is a vapor pressure at that point, and some mercury vapor would be getting into the atmosphere, but this is very, very small. But you can see that here now the temperatures have gone very high before we can even start thinking of mercury becoming a saturated liquid. So for instance, at 100 kilopascals, which is here, the saturation temperature of mercury is about 600 something Kelvin. It's fairly high temperature before mercury will begin to boil. And on the right is sodium. And here you can see that at 100 kPa, sodium will melt at about something like 1150 Kelvin. Fairly high temperature when it melts, and after that it can boil or change phase at constant pressure. But the pressure is increased, it does the same thing. So all these substances are basically showing us the same thing, that you increase the pressure, the saturation temperature increases, or vice versa, and this behavior ends at the critical point for all substances. So we'll now look at a few more charts to tell you that this is not just the case with materials like these. And one would ask, why are you bothered about sodium? Because that sodium is the main material which is used as the coolant in fast breeder reactors or breeder reactors in the nuclear industry. So the first reactors that are being built, the core of the nuclear reactor is surrounded by liquid sodium, or maybe liquid sodium plus liquid potassium, and we need to know the thermodynamic properties and the transport properties of those materials in order to work with them. We will look at one more set of materials and see how their properties are, and then we will move forward. So here's the picture. Okay, here's the plot. It may not look very clear, it is not very good, but what it has is that on the x-axis is temperature here in degrees Celsius, going from 0 degrees to 2800 degrees Celsius. Okay, fairly high. And on the y-axis is pressure, but now the units of this pressure are very, very different. What you see here is pressure in millimeters of mercury absolute. So we know 760 millimeters of mercury is 100 kPa, 1 bar. So that will be something like, this is 100. So this is that dashed line here is likely to be at atmospheric pressure. So you're looking at pressures which go below that, 1 millimeter of mercury. This is one thousandth of a millimeter, 1 micrometer of mercury, 1 nanometer of mercury, and even smaller than that. So you're looking at very, very low pressures, which means that you're looking at very high degrees of vacuum. And that is where you are seeing all these materials being plotted here. Nitrogen, oxygen, carbon dioxide, and water are at this extreme end, followed by mercury. We just looked at that. And then we have a whole bunch of lines with similar shapes, with different magnitudes though, starting with cadmium, zinc, magnesium, calcium, lead, aluminium, copper, gold, iron, titanium, platinum, magnesium, tungsten, tantalum, chromium. So practically every material that we use in engineering is on this chart, and it all behaves in exactly the same way. The big difference is that for these metals, we get saturated states at very, very low pressures and very, very high pressures. But the behavior is the same. And so one can ask, why do I need to look at the vapor pressure curve of, say, in this case, a tungsten, W? But recall that earlier we had incandescent bulbs, and the bulb in the olden times, the bulb was evacuated because of vacuum. So tungsten was heated to a high temperature, something like 2500, 3000 Kelvin. And if you saw that the bulb goes fused, it is because that solid tungsten at that temperature kept evaporating, went into the vapor phase, the diameter of the wire kept going down, it got more hot, and at some point the bulb goes fused. That's what we say the filament breaks. So there are many such cases and many manufacturing processes where we deal with plasmas. For example, plasma deposition on a material, we get very, very different and very desirable properties. Where we deal with materials like chromium and nickel and molybdenum and all that, we are looking at very high temperatures and would like to work with very low pressures, create a plasma, and you do plasma processing of materials, which is a very key technology today in the type of new materials and new processes that we are seeing around us these days. So that's where these properties become important, but bringing it into thermodynamics is that they all behave exactly the same way that what we have learned about, say, water that we started with, or butanes and pentanes and all of that. So that was the vapor pressure curve that we had looked at last time. Okay, now we go on to the other types of diagrams that we have to deal with. And what we have said now is that to get two independent properties, I can have either V, H, S. We can have any of these properties, V, U, H, and S. Any two of these are always two independent properties, no problems. P or T, and any of these are always two independent properties, no problem. But in saturated state, it has to be either any two of these or pressure and any one of these, or temperature and any one of these, or any of these with X. So X with any of these properties, P, T, U, V, H, S, this will constitute two independent properties. And when we do problems, we get different combinations of properties coming in. We should not get flummoxed, and we just simply ask the question, do we have a saturated state? If yes, then we have to look at all of this. If no, any two of these properties are good enough. If the state is completely defined, it may be a little more difficult to get properties. If, say, you are given U and H are given, we automatically know that I have two independent properties. The only trick is, how do I get S, P, and T? And this is a little more tricky. A good software package will get is no issue at all. You just put these numbers, it will tell you what it is. Okay, so that will give us the complete details about states of all these vapor, liquid, and mixtures. Now we look at some other properties, property diagrams. beginning with the pressure and specific. This diagram is very popular with users in refrigeration, air conditioning, and those type of cycles. And by looking at the diagram itself, people used to solve problems in the good old days, like 25, 30 years back. Today, of course, you can do all of that on a computer or even program it. But one needs to understand what is the diagram telling us and how do I know that I'm doing the right thing, and in case I did a mistake, how do I correct it? So I'll briefly describe what is the appearance of this diagram, what are the different regions on this diagram, then I'll show you some real pH diagrams, and then we'll see pH diagrams for many other substances. So the y-axis on the pH diagram we have P, and on the x-axis we have specific enthalpy H. And if we do the same thing what we did earlier, that is we plot all the saturated liquid states, then we will get a bunch of states which are something like this. So this is all x equal to 0. So what we have done is we have taken this pressure and asked what is at this point, it is this pressure, and at that pressure what is HF. So we have plotted P versus HF. That's all we have done, nothing else. And now we do the same thing with P versus Hg, the saturated vapor state. And this graph will give us a bunch of states that have approximately this shape. And this is all x equal to 1, and what we have plotted is pressure versus the dry specific enthalpy in the dry saturated state. And the critical point is right at the top of this, the critical pressure. And this graph will of course always end on the lowest point, it will be the triple point. So except water, for most substances we don't get anywhere close to the point where we start seeing solid, except maybe carbon dioxide in that case. And so in many diagrams, the triple point line and what happens at the bottom is not even shown. But it is there, we don't need to be too concerned about it. So if we draw these lines, we get this shape. One on that side and one that comes something like this. So this has this particular shape coming inside this region, and we will now start giving it a name, because this is what all diagrams will look like. This we will call as the dome, or in many cases this is the saturation dome. So we'll use this word very frequently, that the state like inside the dome is the wet state, which means that the state is somewhere in this region inside here. So that's inside this is all our wet saturated states. X equal to 0 is here, x equal to 1 is there, and at constant pressure, if you keep heating it, you will go like that from x equal to 0 equal to x equal to 1. Constant temperature lines will go something like this, then they will continue like this, and then start going down there. So this is T1, and like that there will be a similar line T2, and then the critical isotherm there will be a line T3. So this is what one sees. So this is T2, and like that there will be a family of these lines coming on this. And along with that, we can also plot constant entropy lines. So that was T, and constant entropy lines on this line diagram, they end up going something like that. S1, S2, and so on. So what does this diagram tell us? This side is the compressed liquid, this portion here, or the subcooled liquid. This side here is superheated vapor, and above this is supercritical liquid. Or dense fluid. That processes like heating and cooling especially in a flow process. And an example of that is, say, the air conditioner evaporator, in which we are pumping in the substance, it goes through all the tubes, comes out. In the real case, there will be some pressure drop. So the outlet pressure will be slightly less than the inlet pressure. For the time being, let's not worry about it and say that there is no pressure drop. In the first cut analysis in thermodynamics, we assume that flow processes involving heating and cooling and no work transfer, these are constant pressure processes or isobaric. That's an important assumption we'll make in this course, that wherever we are going to look at a flow system and we look at either condensation or heating or cooling, we say that it is isobaric, which is an approximation to the extent that we are neglecting pressure drop in the pipe. Pressure drop is what one would have learned in a fluid mechanics course, the same thing. It's a good first assumption. When you start doing real systems, then of course you will start worrying about pressure drops, but they can also be shown on this diagram. So let's ask the question, what happens in the condenser of your air conditioner? Well, we start with a superheated state, say somewhere there, which is what we got after the compressor. And then we put it into a set of tubes on which we blow ambient air. The temperature of the vapor inside is more than the ambient temperature, so it starts rejecting heat and it gradually keeps cooling down and it goes through all these states like this. At some point it becomes a saturated vapor, we continue cooling it, and at some point we say, okay, enough cooling is done, and this is our exit state. So this line, this 1 to 2, is your ideal condensation process in the air conditioner. What the real process will do, there will be some pressure drop along this line, so the final state will be at a pressure slightly below this pressure. So we can say that it came somewhere there, and so this line would be somewhat off from here. That's how we show a state on these state diagrams, and we show a line with an arrow to depict what is the process. A solid line means that this is a reversible process. If the process is irreversible, this will have to be a dotted line. And the nice thing about this diagram is that if we are able to get these two states plotted on this diagram, then we can say, well, what is the enthalpy change in this process? Well, if you do the mass conservation and first law analysis, you'll get a relation that heat transfer rate is the mass flow rate multiplied by the enthalpy difference between the inlet and the exit states. That is quite nice because you can just go down this chart, look up this value of the specific enthalpy, go down this point, look up this value of the specific enthalpy. We can get H1, we can get H2, and the difference of this is the enthalpy drop during the process. That multiplied by the mass flow rate is the heat transfer in this process in steady state, no change in kinetic and potential assumptions. That's a nice thing to know. The next thing that happens in the refrigerator, and we can now see yet another process that happens there. In the previous module, I discussed that if potential energy changes are very small, kinetic energy changes are small, it is adiabatic, no work transfer, steady state, then inlet and outlet enthalpies are equal to one another in a throttling process. So in this diagram, H equal to constant will be a vertical line, and that's what we do in a fridge or an AC, that after this thing, the fluid is throttled and brought down to a low pressure. And this process will be shown by a broken line because throttling, no matter what, is a hugely irreversible process always. So this brings us to another state, state 3, and it tells you that, okay, if we know the specific enthalpy at 2 and the final pressure of throttling, then I know that H3 is equal to H2 because it's the isenthalpic process. P3 is given to me. I have two independent properties, we can do the rest of the calculation. It is at this state that the refrigerant enters the evaporator where the cooling takes place and keeps getting heated up, and it goes through a bunch of in the room, and the wet saturated refrigerant kept getting heated its dryness fraction kept increasing, became X equal to 1, and then became a superheated vapor. That's what was happening. And to complete this refrigeration cycle, we say at this point it enters the compressor, and if we assume that the compression process is reversible adiabatic, it means that it is an isentropic process, then the process inside the compressor will go along an constant entropy line. This will again have to be a solid line, and that is our compression process. And so very nicely we are able to visualize what this diagram looks like. And also we can even get quantifiable data. Earlier we had to look up the charts and do interpolations. These days we can even make this whole thing in a software, and by touching the points on the screen we can just get all the data from there. Or to be more exact, we go to the tables, input all these properties and get much more accurate data. That is the best thing. So that is the pH diagram. Now I'll show you a real pH diagram. And there are lots of lines over there. But what we have to see mainly is that pressure is on this axis, a logarithmic scale in megapascal. On the x-axis, it is specific enthalpy in kilojoules per kg. And you can see these dark lines. It says saturated liquid line. Here it goes up. And on this side, it says saturated vapor line. This goes up over there. And at the top is the critical point for water. And from this, you can see there are many other lines on this. So let's spend a few minutes trying to figure out what they tell us. The first is a set of lines that you can see here. It says 0.1, 0.2, 0.3, 0.4, and 0.9. And here it says x is equal to 0.5. So these lines inside the dome are lines of constant dryness fraction. There is another set of lines which are going here, slightly at a larger angle than that. S is equal to 5 kilojoules per kg Kelvin. So these are lines you can see here everywhere. This is S is equal to 8 kilojoules per kg, 9.5, 8.5. These are constant entropies lines. This is H, constant S lines, constant X lines. Now X lines of course are inside the dome only, they are not outside the dome. Then you can see these are the lines which are going constant specific volume lines. So these are those lines. 5 meter cube per kg, 0.03 meter cube per kg, and so on. And these funny looking lines coming from the top, these are constant temperature lines. And what I was just drawing are these lines over here, which says like 550. So this is the line that is coming at 550. This is the line coming at 500. This is the line going at 450. So they're almost vertical lines. In the compressed liquid part, become horizontal inside it, so they have not been shown, but we know that it is the same thing. And then from there it further goes down and comes 504. So on that pH diagram, this is what we were looking at. We have constant temperature lines, we have constant entropy lines, and we also saw inside the dome constant dryness fraction lines. And of course we are also, I haven't drawn here, but also constant specific volume lines. And the substance that I'll put up here is oxygen. Simply because now the scale of temperatures is completely different on this, but you can look at the shape of this, it's exactly the same. Okay, so here we are. Pressure in megapascals, 0.1 megapascal, 1 megapascal, 10 megapascal. Specific enthalpy, H. And same thing we see here, saturated liquid line over there, saturated vapor line over there, just like what we had seen qualitatively there. So this is your saturated vapor line, and on the other side we end up getting the saturated liquid line. Inside the dome we have the similar things, 0.1, 0.2 like this. This is constant dryness fraction over there. Then 1.5, 1.75, these are all constant specific entropy lines. Outside these are constant specific volume lines over there. This is S equal to 3 kilojoules per kg K. And then we have constant temperature lines, which is like what we have drawn there. This is a constant temperature line and another constant temperature line. The temperatures here are very low, 150 Kelvin, 135 Kelvin, 120 Kelvin, 105 Kelvin. We are looking at very low temperatures. But look at this thing here. Ambient pressure is 0.1 megapascal, and so it comes over here. So at 0.1 megapascal, what we see is oxygen at in this condition is in a wet state, which means that at this thing, if we cool it down, and this temperature here is 105 Kelvin, this is even below that, it turns out to be about 77 Kelvin. So 77 Kelvin, 100 Kelvin at these pressures, oxygen behaves like has a liquid and a vapor state, and you can start getting wet states in this. And the reason for saying this is that in the cryogenic engines, picture of which I showed you yesterday, the oxidant is liquid oxygen, which is filled at this state. So we need to know what is the specific volume there, how sensitive is it to temperature, what is the specific entropy, what is the pressure and temperature to which I need to cool it, and then we know how much is the volume that we need to have in the solid rocket motor to put that much liquid oxygen in it. There are many other uses of oxygen. For example, a medical oxygen cylinder that comes filled at 150 bar. 150 bar is 15 megapascal, which is somewhere here. And if you say what is ambient temperature, that's about 300 Kelvin. So it is 300 Kelvin line is here. So a medical oxygen cylinder is at this state here. Highly superheated vapor, but substantially high pressure. So we need to think, is this compression going to deviate the behavior from what we are seeing here? Okay, so this is for oxygen, and now we'll see for a few more substances and see one important aspect. Okay, let's see this. Same thing what we have seen so far. Specific enthalpy on the x-axis, pressure on the y-axis, the logarithmic scale. But what I've done here, and this is data taken from the tables and I just made the plot myself, is this side, this is the chart for water. On the left side are saturated liquid states for water. On the right side, sorry, this is not water, this is ammonia. This is for ammonia, and on the right side is dry saturated vapor state of ammonia. And then we have put other things here. So this side is, you have propane, and then we have R12 and R22 over there. So what we are seeing here is they all have the same shape, but in making this drawing, we have to be very, very careful, because in all these cases, specific enthalpy, which is here set to 0, is decided quite generally as per the wishes of the person making the property tables. In these materials, the specific enthalpy HF at 200 Kelvin has been set to 0. And so we could make all these property plots of different substances on this. Water tables that you see, there the specific enthalpy of liquid, saturated liquid water at triple point is set to 0. So I cannot just make that plot and plot H of that on this. They will look fine, okay, but actually they are quite different there. The whole thing will have to be shifted quite a ways out. The other thing that this sort of a picture tells us is that what are the substances that have somewhat similar properties. And this issue came up 20 years back when R12 as a refrigerant was banned because of ozone layer depletion. An immediate question people started asking, that what is the material that I can put in my refrigerator and air conditioners. So people started looking at these properties and said, look, let's see what all materials we have. We have propane, we have butane, we have R22, 23, 14, so many hydrofluorocarbons. And we start looking at all the properties and we find that two materials which are very similar in properties, we can substitute them with one another provided all the other things don't come in the way. For example, there is no corrosion or reaction with the oils, or it becomes toxic, then we won't use it. But if those things are also okay, then what it means is that you can take the existing refrigerator or the existing air conditioner, throw out R12 and put it your new refrigerant, and your fridge and AC is good enough to keep working on. And that's what initially was done. But as time goes on, we came from R12 to 22. Now 22 has to be banned and removed. So we are now looking at even more refrigerants which we can change. And that's how you see in the market today 134A in refrigerators. 5 years from now, even that will be probably phased out and you will have something more coming in. And this is the basic starting point from which we do the design and engineering of all those devices. So that's why I put this diagram, and the idea is that beyond just looking at it and getting properties, it tells us a lot more about how these substances behave and which can be used in lieu of the other ones. Okay, so that was the pH diagram. We now go to the next type of a diagram, which is again very popularly used, is temperature entropy diagram. On the y-axis is temperature. And on the x-axis is specific entropy. And again, making this plot, you have to have the same caution that we had with the pH plot. Once you have set specific entropy at a particular point to 0, specific entropy also gets set to 0. So specific entropy has the same issues, that specific entropy of nitrogen has got some value, specific entropy of water has some value. The two are not on the same scale. Temperatures are on the same scale, specific volume is on the same scale, but specific enthalpy, specific entropy are not on the same scale. We have to have a common reference point for everything, only then we can compare them. Okay, so now let's look at the TS diagram. And we do the same thing we did for the pH diagram. And what happens here, if you look at any of these substances, what we see is that the saturated liquid states all come on a line like that. This is all the saturated liquid states. Saturated liquid line is called, or x equal to 0. And we continue the same plot. We take all the properties of the dry saturated vapor and make a plot, and it looks something like that. This is all x equal to 1, and we can join all of these. This is the saturated liquid line, and this side we get the saturated vapor line, and at the top is the critical point. So this is the dome. Again, and what happens here is we can now ask for what constant pressure lines. We can ask for constant enthalpy lines, constant dryness fraction lines, and constant specific volume lines. Okay, so easiest one is x, and this will follow exactly the same style as we had earlier. At any given temperature, x equal to 0 is here, x equal to 1 is here, it is increasing monotonously here. Same with every pressure. So constant dryness fraction lines will all look like that. So these are constant dryness fraction, and they are always inside the dome. Now we ask for constant pressure lines. That's what happens is we do the same, that TV type of a thing here. It starts from here and very quickly, say, comes to the saturated liquid state. Then the pressure is constant, and then from here the constant pressure line begins to go up. Then we come another point there, and then again it starts to go up. At even higher pressures we come there, and finally at the critical pressure we get this critical isobar. So pressures below the critical pressure and temperatures below the critical temperature, we see the phase change taking place. So constant pressure heating from this state will first take this to a saturated liquid state. The specific entropy is increasing. Then it will be followed by constant temperature evaporation, and then it will become a superheated vapor and then continue on this line. So that's what the constant pressure heating line looks like. Constant pressure cooling line will be exactly the opposite of this, which in our TS diagram was a nice straight line. Here it has become a little more curvy line. And that this was state 1, this is state 2. From state 2, we undergo an isentropic process. Isentropic process means S is constant, and this will be achievable in an ideal situation in a turbine or a compressor, nozzle or a diffuser. These are all isentropic processes, and these are all slow processes. But that doesn't matter. So what it means is that if S is constant, a turbine or a nozzle attains states which are on this line, anywhere. And then depending on if the pressure was there, this will be the state. The pressure was there, this will be the state. Pressure was there, this will be the exit state. And this diagram tells us that if any of these devices were non-ideal, that's what we learned in the laws, then there will be an increase in entropy, which means that while the ideal turbine will have come like this, the real turbine or the real nozzle will go like that to that point. And that will not be a solid line, so this has to be a dotted line. So from here to here, the turbine, ideal turbine will be like this, the real turbine will be like that. The compression process will be exactly opposite. Ideal compression will be isentropic, it will go up. The real compression will of course have an increase in entropy, so the line will go that side. So that's how the TS diagram helps us in visualizing all these work consuming devices. The same is true even at this end, that when you have compressed liquid. So if you are pumping water from this pressure to this pressure, this will be the ideal pumping, this will be the real pumping. And the trouble is, you will see in a minute that all these lines on this side, they are very, very close to one another, and what we draw here as pumping as this state is the ideal one. This is the isobar, and real pumping will be like this. This is a big exaggeration on what we can actually see on the diagram because the lines are very, very close, but in the real world, this is something we will have to take care of. Okay, so that is the lines of constant pressure that we looked at. Now we want lines of constant enthalpy, and what happens is that these lines go like that. So these are constant enthalpy lines. And what it tells you is that if you are going to do throttling from here, that's an isenthalpic process, then the states that one would get will be all along that side and not along this side. Throttling is an irreversible process. Entropy has to increase, so the states will lie to the right and not to the left. You cannot throttle a substance to a higher pressure. It is always to be throttled to a lower pressure. So these are constant enthalpy lines. Specific volume lines are also somewhat similar on this, but of a different slope. So that tells us everything that we wanted about the TS diagram. And I have illustrated this with a heating process, which is like a cooling process, a turbine and a nozzle, and also the throttling process of this diagram. Okay, now we will see the real TS diagram. Okay, you see a lot of lines over there. This is specific entropy. It is 0 here, which is saturated liquid at triple point. This is the triple point line of water, and this is temperature in Kelvin. So this is for water. And the shape of the dome is like what I qualitatively shown. And inside this dome, you have the same thing. X is equal to 0.1, 0.2, 0.3, constant dryness fraction lines going that way. Then you have P equal to 0.1 megapascal, 0.2, 5, 10, 20, 100 megapascal. These lines are going up there like that. But notice one thing, that this is 20 megapascal, 50 megapascal, 100 megapascal. So suddenly within this small range, we have had a huge increase in pressure. This side we are going lower and lower in pressure, 0.1 megapascal, 0.001 megapascal. So we are going like now 1 kilopascal. So these are very low pressures. And then if you see this part, practically they have not drawn anything over here. And we know that all these states on this side, and this is now this extreme line on the right, on the left, is 100 megapascal, very, very high pressure. And this is the saturated liquid line. So pumping water from 1 bar to 10 bar won't even show up on this line. It will be a very, very small line somewhere squeezed in between this here. And that's because the dependence of entropy on pressure is very, very weak. And so we cannot see those lines here. And so although on my diagram, on freehand, we can show all these pumping processes, isentropic and asentropic, if we were to use the real diagram, we cannot even show this, visualize these processes over here, but reality they will be there. And these are the constant enthalpy lines, H equal to 3500. You can see that these lines are going like this. And what one sees interestingly is that as this H line comes in, it is somewhat like a constant vertical straight line here. Then it goes through a turn, and then these lines are pretty much horizontal at this end. Look at this spot. And in a minute we will see why these H lines have become horizontal, which means that H is now 3500 at this particular temperature. So if you pick up any pressure, that doesn't matter, specific enthalpy is the same. It is independent of the pressure, and that's what we will see, that this is what ideal gas behavior actually begins to look like. Okay, so this is the thermodynamic properties of water. And again, now let's see what use I can put this to. And I pose a question that in a refrigerator we use 134A or R22, or in the olden days there was ammonia. Why can't I make a refrigeration cycle or an air conditioning system with water as the working substance? We have steam power cycles, all of them use water. Why not use the water in a refrigerator? And so let's begin to look at this. What will happen? Firstly, we cannot go below 0 degrees Celsius. It will freeze. So we have got to make a compromise and say, look, I will give a safety margin and say I will not go below, say, 6 degrees or 5 degrees Celsius. And that means that we will be something like, you say this was 280, this part is 273 plus 6 makes it about 290. So somewhere over there is the lowest temperature we can get. And then we want to reject heat to the environment, so we want to heat it to temperatures above 55 degrees Celsius, say, if it's the ambient. So it's about 80-85 degrees Celsius. So that makes it 273 plus 85 is about 360 or something like that. So that will be here, say, approximately. So we have to make a cycle which will operate between these points, 360 and this thing. And so it has to have one throttling process. So this will be a condensation process which will happen at the higher temperature. So it will be condensation like this to liquid, then a throttling, which is H constant line comes here, then here, and then goes back over there, and then you compress it. Constant entropy compression. The trouble is that if you look at 360 and you start looking at the numbers that come out, you'll see here that the specific volume is on the order of, it says 100 meter cube per kg. V. So this is very, very big specific volume. This is vapor at low pressure. It occupies a very large volume. So to get the same mass flow rate, we need very, very big pipes, many meters in diameter, before we can even make this thing work. And to get any reasonable amount of cooling effect, this whole system will become very huge, very bulky, and so you'll have to make a compromise and say, look, only if I can make a compromise and use all of this in a very compact way, then I will use water as a refrigerant. But otherwise, water as a refrigerant is in fact not possible for freezing at all. I can only use it at best for air conditioning, and that is the central idea of what is called a vapor absorption chiller or a vapor absorption machine, where water is the working substance. You operate at very, very low pressures throughout the cycle, and you have to keep worrying that air does not leak into it. And that is where the engineering becomes complex. Now, firstly was size. The second thing, all these property diagrams tells us that pressures of water will be very low, much less than the ambient pressure, which means that I can always expect leakages, and leak will be air into the system. And once air leaks into the system, but partial pressure of air goes up, the performance of the system drastically goes down, and we have a big problem. But that is where the engineering challenge lies. This is a very attractive way of doing air conditioning because the work or the electricity that it consumes is very, very small compared to vapor compression systems, which is what we use in fridge and ACs. But that's the implication of properties of a pure substance on what we can do and what we cannot do. Okay, so that was the other diagram that I had. And there's a question here, so let's see. Okay, there is a question which says what will be examples where there will be chemical composition is different at different phases. Okay, I'll come back to it a little later. And I'll come back to it tomorrow after we discuss ideal gases. Okay, there's one more diagram that I will put out. And this is historically a very popular diagram. And a lot of the initial engineering in the early 1900s was done with this plot. And of course, that plot was made by hand. There were no computers or anything. So all these property data were taken and using freehand and using various things, people made nice beautiful curves and made this picture. And that was the mainstay of engineering into the late 70s. That's when slowly computers started coming in. This is called, this diagram has H on one side, S on one side. So this is the HS diagram, and popularly this was known as the Mollier diagram or the Mollier chart. And a whole generation of engineers did design of thermal power systems and other steam-based systems with this diagram. They plotted the points on this, found out what is what, and that's how they went about doing it. Now remember, we're talking of liquid oxygen and all this. This is also the time in the 60s and 50s last century. There were no computers, and the whole design of putting man on moon and launch vehicles was all done by such diagrams. Right? They're quite powerful tools. On this diagram, the saturation dome is like this, but the saturation point is over here. Saturated liquid line is over here. This is the saturated vapor line. These are lines of constant dryness fraction, 0.76, 0.78, 0.86, 0.98. So we get very good discrimination of dryness fraction here. These are lines of constant temperature. These are lines of constant specific volume, and these are lines of constant pressure. So one can draw all the processes that where is the inlet state to a turbine, where is the outlet state, then where is the reheat taking place, where is the condensation, and we can make the complete cycle on this, and then do all the calculations for sizing of the equipment. Nowadays, it's good to know that this is there, and by showing a cycle on this, we get a very first-hand feel of what this cycle is all about, and what are the possibilities where we can improve, what are the things we cannot do on this diagram. That also becomes clear. Okay, now let's go back to our cell. Let's start with the TS diagram. And I mentioned that as we go further and further away, the H lines are becoming horizontal. That means constant temperature line and constant specific enthalpy lines are becoming one and the same. So H is now linearly related to T in some sense. You can look at another way, like if you look at this part of this chart, the lines have somewhat become straight and they are somewhat parallel to one another. Okay. So what that tells us is that that was not the case when we were looking at the lines in this region. Here there are all sorts of funny shapes of the lines, nothing seems to be parallel, nothing seems to be straight, and that is the reason why in this whole region you have very strong non-linearities of behavior of the properties. And that's why we needed to make a very complicated surface like the PVT surface that I showed last time. We fit 60-70 constant equation to that, and then we are able to compute all the properties. But what this thing tells us is that life has become much more easier. You don't need such a complex formulation anymore. Maybe you can do something much simpler over here. Don't worry about this part. So that is what is happening. And same thing happens on the TV diagram also. So here is what is going on. If you make the TV diagram, this curve was like that, and you had the critical point at the top. as we go far away, all these constant pressure lines that we were looking at, they become nice, straight, and almost like parallel to one another. Similar thing was happening on the TS diagram. So what it tells us is that somewhere there, and we can say that roughly here there is a region, and there's no hard and fast rule that this is like this and this is in that part. That's why I'm drawing this a little bit zigzag. That here somewhere we can start looking at the substance as a gas, and in this whole region we have to think of it as a vapor. And these are the two very distinct regimes. And within this gas we will now see ideal gas and real gas. But the fact is that in this condition where there is a vapor-like behavior, we should not even think of PV equal to RT. Completely wrong. And that's why all property diagrams end at some point and they do not give the chart properties beyond that, because then it is presumed that after these range of pressures and temperatures, the substance behaves like an ideal gas. You can start using ideal gas equations of state and you can forget about this part. And as I mentioned yesterday, we have several applications where you have the application entirely in this region. So we don't even come into this part. And then we have applications which are entirely in this region, maybe sometimes touching this region, but largely in this. So those have to be treated as vapors, and those other cycles have to be treated as gas. And those few examples where you have some behavior here and some behavior over there, we then have to do a mix and match and very carefully see how properties get added up to give us the total change between this state and this state. Okay, so what we will now do is say, well, we have defined, say, we have got the first idea, what is something going to be like a gas? And now we continue with this discussion and say, when on this diagram can I say that the substance has begun to behave like a gas? And that tells us that basically we are looking at temperatures in this range where T minus T saturation or the degree of superheat is large. We have not yet defined what is large, but we say that look, if we are far away from this, that means you have heated it a lot more than this saturation temperature here, you can start thinking of this as a gas, at least as a first of all. And if that condition is not there, it cannot be a gas. So now we will do is first look at what is the criteria that we have to decide in some more quantitative way whether the substance can be considered to be a gas or it can be considered to be a non-gas. The theory for that goes like this. We look at the critical point. And we say that relative to the critical point, where does the state lie? And then we will define a series, a group of states, which we can say are good for ideal gas behavior. Okay, so the first thing we do is, we say that at the critical point, we define a new property which we call, say, reduced pressure. We call this PR, defined as the actual pressure at that state divided by the critical pressure. And similarly, reduced temperature. T, this is the reduced temperature, defined as the actual temperature divided by the critical temperature. Pressures are always absolute, so we don't have a problem. Temperatures, be always careful. All temperatures must be in Kelvin only for this particular case. We cannot have a negative reduced temperature. So this is the first thing we define. And then we say the ideal gas assumption says that the equation of state is PV is equal to RT. or if we make a three-dimensional plot, then R, which is the constant, is equal to PV by T. So we can pick up P and V to figure out what is T and make a plot, and we can see that instead of that complex looking three-dimensional PVT shape, we start now looking at a very nice, well-behaved, smooth PVT shape. That means we are in that ideal gas state. And the question is, why did this substance behave like an ideal gas? And that means that it started doing those things which we talked about in the beginning of yesterday's lecture, that these molecules are now far away. They are behaving like rigid spheres. There is no other interaction between them, no gravitational attraction, no nuclear repulsion, no electromagnetic forces. They are moving in a random way, and they are undergoing perfectly elastic collisions. That's why we said that this is now going to behave like a gas. This behavior begins to deviate sharply when we are in this region, and the moment we are in the saturated state and liquid state or the supercritical state, it completely breaks down. There will be some regions of the vapor behavior where we can still say that ideal gas is approximately valid, or at least a correction to ideal gas equation state. So physically, this is what happens here. This does not happen in this part of the property. So what we do as a first case is that we say that if we are far away from this, way away, like in the case of nitrogen. Okay, so if you make the plot for nitrogen, and I'll show you a picture. Okay, what I've done here is something beyond what you see in the charts, in the sense that I have equalized the reference condition for nitrogen and water. And I said that specific entropy of that both substances at 0 Kelvin is 0. And with respect to that, I replotted SF and SG on the TS diagram. So now we are looking at a consistent set of specific entropy for two very different substances, whereas according to the tables, nitrogen is reference to some temperature, water is reference to 0.01 degrees Celsius. We cannot directly plot the two on the same diagram, but this is consistent now. So here is what you see. This is nitrogen, the TS diagram of nitrogen. This is the TS diagram for water. And what happens now is that let's take the case of an inlet of a gas turbine. And I've been mentioning that temperatures there like 1400 Kelvin, 1600 Kelvin are now typical in aircraft engines and also land-based power generating units. If that 1400 Kelvin is over here, then for nitrogen, we are way, way far away from this saturation dome. In fact, even if you look at water at that state, we are still far away from this thing. So 1400, 1700, 1900 Kelvin, which are now temperatures that we are talking of in combustors and burners, we are far away from this dome, and we can say that, look, I'm far away from the critical point. Anything like this, I can quite happily accept that this is ideal gas behavior. In fact, that's what we do for nitrogen. Critical point of nitrogen is 126 Kelvin. We live in 300 Kelvin plus type of a thing. So we are about more than 2.5 times the critical temperature of nitrogen. So reduced temperature, the way we just defined a few minutes back, for ambient condition for nitrogen will be about 2. And so look, we are far away, and so we presume that air around us, and for all purposes of calculations and analysis, we treat air, or nitrogen part of air, as an ideal gas. Do the same thing for oxygen. The curve will be lower than this slightly, equally good for oxygen to be treated as an ideal gas at ambient conditions. And we go actually one step further and we say that, look, nitrogen and oxygen also happen to be very similar molecules, at least in the physical sense, not the chemical sense. And so we will define air as a new pure substance, a pseudo pure substance, and assign properties to it. And that's what you see in the air property charts. As a first analysis, that's a very good thing to have. But this is what happens, that you have one substance at a very low temperature, that means states where water behaves like a saturated state are the same pressure and temperature at which nitrogen behaves as an ideal gas. And in a combined cycle power plant, both are happening in the same system. So we've got to really think twice as to what we are going to do and how we are going to show things on this. Okay, so that's what I was trying to show there. And what we do is we make one change to this ideal gas equation by defining Z, the compressibility factor, and put the equation PV is equal to Z. So Z begins to play a factor when that ideal gas behavior, which is the molecular behavior, begins to undergo a change, which happens at higher pressures and lower temperatures. Okay, so then we say, look, I'll make some correction, and that amount of correction that I need to make, this is a function of the pressure and temperature, or here we will put reduced pressure and reduced temperature. And once we do that, we get a little better in using a very simple equation of state a little further down. So we can say that, look, now I don't have to stop here with PV equal to RT. If I start using PV equal to ZRT, maybe I can cover this more region also. Z is, in this region, Z is one ideal gas behavior. In this case, Z is somewhat off, but I can calculate it and make a correction. And you can continue that logic here also. Only difference is that the correction that Z will bring to PV equal to RT is very big. In fact, here it will be correction of the order of 100. So it is not 1%, 2%, 5% deviation from ideal gas, it's a huge deviation from ideal gas. But that forms the basis for a unified set of equations for the entire range of behavior. Okay. I'll come back to the questions in a few minutes. We'll just wrap up this thing and then I will take all the questions. Okay, so now what is Z? The thing that happens is we start with what Z is actually is PV upon RT. But now we should be clear that V that we are getting is V actual upon RT. That means your medical oxygen cylinder at home, it has got a certain specific volume. We know the pressure and temperature at which it exists. So the actual specific volume we know because the mass and the volume of the cylinder were known. Independently, we know the pressure and temperature, and ideal gas equation of state tells you that V ideal gas is equal to RT upon P. This is different from this, or from this. This is V actual. And the ratio of these two is what we call the compressibility factor. So this can be written as the actual specific volume divided by the specific volume predicted by the ideal gas equations. If Z is equal to 1, ideal gas. But exactly 1 we get very rarely. So you say, okay, plus minus 0.01, that's good enough. That's an ideal gas. But then there are some cases where you say, look, I can tolerate plus minus 0.05. A 5% uncertainty in Z will cause a certain uncertainty in H and S and U. And as a first calculation, it's okay for you. But anything more, that will not be right. And why that doesn't get right is when you do this plot, Z versus pressure, and say we do it for water. This is 1, and below that becomes 0.5, 0.75, something, and this is 0. So at certain high temperatures, this will become like this and it will go off. So these are the Z values you get. Then it will become like that and start going up as the temperature decreases. This is reduced temperature, say 2 TR, reduced temperature is 2, then this reduced temperature is 1.5, reduced temperature is even less, it may go here, reduced temperature of 5. When you come down 1.2, 1.1 like this deviation from Z equal to 1 becomes very, very large. Now we have a problem. And if this was a sort of a plot for water and we could get Z as a function of pressure and temperature, then we would have to get a similar plot for butane, another plot for oxygen, another plot for everything else. And life would be very, very complicated. But nature has its own beauty, and instead of plotting P and running parameter as T, so T is increasing this way, we change the coordinates, and instead of P, we plot the reduced pressure, and instead of T, we plot the reduced temperature. Then something quite elegant happens. So this side is reduced pressure, and this will be logarithmic scale 0.01, somewhere here 0.1, 1, 10, 100. Reduced pressure has no units, so no problem. We'll put Z over here, 1, 0.8, 0.7, 0.6, down to 0. And now we will draw lines of constant TR and what Z they give. So the first thing we'll do is we mark something which we would like to see, Z equal to 1. And we start saying that if we reduce temperature is say 2, it will be something like this. This is 2 TR. If you go to 5, it may go up slightly up here and then take off. So this might be 5. 1.5, it will start there, come down, and then start going off. This is 1.5 TR. 1, it will come there. And so 1 will actually be at the critical point, so it actually will come somewhere there, around 0.2, and then go. So you can consider this to be like 1.2, this to be 1. And below that, you have a curve. So this will happen when it is 1. Sorry, so this line should be like this, 1 and 2, so somewhere here. So reduced pressure is 1, reduced temperature is 1, and you get Z critical, something like 0.27 or something like that. And below that, we start getting a curve like this. And at even lower reduced temperatures, you actually start getting up to this point, and then you have a saturated state, and then again from here it starts to pick up. That's the type of behavior that emerges, and we'll get the exact numbers a little later. But let's see what does it tell as to which are the conditions under which we can safely assume a material to be an ideal gas. Okay, so the question is, in which part of this chart can I say that ideal gas is okay? And so we look at the case where Z is equal to 1, and they say, okay, wherever Z is within a band, ideal gas is okay. And so one of the regions that emerges is right here. So if reduced pressure is very small and reduced temperature is say greater than 2, then we can safely assume ideal gas behavior. And that's precisely the state under which the atmosphere falls. So we are quite happy that whatever we do with air, PV equal to RT is a reasonably nice thing to do for most things that we are looking at, unless we are going to vary air pressures. Then we see another region here, that even if you go to reduce temperatures to a lower value and reduced pressures are below 10, then also we can say that is ideal gas behavior, but now variation will be about plus minus 5%. Here we can be sure that as you go further away, here this side, variation is well below 1%. It's quite nice. Here, not so nice, but it's okay. And at higher pressures, no, because these curves are very steep, they go up. So we cannot assume anything beyond reduced pressure of 10 to be an ideal gas. And then again, even if we say that it is reduced pressure, reduced temperature is 2, even if it were a saturated state, then also it is not okay. So we can only look at this part where some saturated states will also come as ideal gas behavior, but the saturated liquid state, which is this line, this has got very large Z or very small, cannot be considered to be an ideal gas. Okay. So that's what we have introduced now, the chart which is known as the generalized compressibility chart. And people have done a lot of curve fitting on this and come up with various different types of equations of state. A summary of that is given in the notes, and you can look up that as you start getting away and away from ideal gas behavior, you can use better and better equations of state as long as you are in the gas or the vapor phase, after which that equation of state is not valid at all. Okay, so we will stop here and take up questions now. And the question that we have here is, this is, please explain the critical pressure and critical temperature. Okay, so let me put this up again. Now I'll use any of these charts there instead of my own pictures. Okay, so here we have a TS diagram for water. And what we are seeing here is that this is the critical point. At the critical point, the difference between vapor and liquid behavior has disappeared. There is only one state, and that we call the critical state or the critical flow rate. And any state above this, to the left of this, to the right of this, is also a single homogeneous state. Second thing, if you heat it or you cool it, there is no clear physical difference between two regions, two phases with drastically different densities. That doesn't happen. So that is what's the first instant where that doesn't happen is the critical state. Below the critical state, you have any pressure or temperature below the critical state and you heat it or cool it, we are likely to get a mixture of saturated liquid and saturated vapor. So that's one way to look at critical state. The second thing you can talk of the critical state is that above the critical temperature and critical pressure, which are unique properties of every substance, we cannot get a saturated state. A saturated state is possible only at pressures and temperatures below the critical point. That's another thing we can come across. And since there is no quantum change in physical properties from liquid to vapor, we only see a continuum happening there. So it means that properties can be described by reasonably nice equations without discontinuities, which is what was happening in the saturation states. So mathematically and formulation wise, that is the other thing to do. I should also mention though that equations of states and the plots that we have, they are pretty good in most places, but right near the critical point, we have a singularity in the mathematics, and it's very difficult to do the programming. And so now gradually people are saying that, okay, let's not get too tied up by forcing the critical state conditions to be there, but it's okay that in this region, the substance is a homogeneous thing and we do not see any phase change below that pressure. Okay, so that's something more about the critical point. It's a property of every substance, a unique property, and that unique property means you have a P critical, a T critical, a V critical, S critical, H critical. They are all fixed. They cannot change, and for a substance, they are already there. Okay, so there are many practical situations where we have to worry about the critical point. Large power stations, the new ones that are there in the country in the last 5-6 years, they all have water which has been pumped to pressures above 220 bar, 280 bar, 300 bar pressures. They will all be in lines that go beyond this. So the heating is done there, and it means that the physical properties are not changing, so the heat transfer properties will not change very drastically. So your engineering of that boiler is very different from the engineering of this type of a boiler. That's the practical implication of a critical state. Okay, so that was a little more explanation of the critical pressure and critical temperature. How to calculate the maximum vibration energy of molecule at superheated state? Oh, okay, there's a question which says how to calculate the maximum vibration energy of a molecule at superheated state. Well, if you want to look at molecule to molecule thing, it's very difficult. If you want the averages of that to be done, you have to go to statistical mechanics, use the Boltzmann equation, use the partition functions, and from there you will get all of that. Most cases that we look at in classical thermodynamics, we don't need to go into that. Okay, then the question it says, please explain the significance of reduced pressure and reduced temperature. Okay, the significance is that we are able to move away from the specific variabilities that are there from substance to substance. Like I showed in this picture for nitrogen and water. See here, this is nitrogen. The actual critical point is over here. Water, the critical point is here. From a mathematical standpoint, it would be nice if all of these could be made into one equation. And there are many instances where these things can happen. There are some cases where this does not happen. The one case where it does happen is what I've just explained, is that the actual pressure, we normalize it on the critical pressure. And fortunately, what that does for us is that you get a very nice single compressibility chart for all materials. It's not that every thing is lying exactly on this line. There is a variability around this from substance to substance, and you're looking at plus minus 2% type of a variability in making the generalized compressibility chart in the first instance. So that's what the reduced pressure and temperature actually helps us in that we get a common set of pressures and temperatures for which we can compare materials, various different types of materials. Just by looking at their absolute properties, we get very funny looking pictures, which is very difficult to generalize. So that's why we do this. The second thing is also that when we write the property charts, it is always nice to move away from absolute values into normalized values, and then you get an equation which has got much larger applicability than that equation which has properties for that particular substance. So we are looking at a little more versatility in the same equation being used for many substances, and that's where this PRTR come in. Okay, then there is a question: what are the modern techniques that we use to analyze gases and vapors thermodynamically? But the good old thing is still the best, that we make a closed system and any new substance that we develop, we put into it, heat it up to different pressures and temperatures and measure its properties. And then make a curve fit to the PVT diagram and get properties from there. What has changed in the last 50, 60 years though, is that the quality of instruments has improved. The mathematical techniques that we have, they have improved a lot. And so we think that we can do a lot better, but still, some of the property diagrams, say especially for water, which was the first one to be studied, which came from way back 70, 80 years ago, some of the experiments done at that time are still among the best experiments that people have done. So doing a good experiment is not about how many more modern techniques we have, but how well we are able to design a thorough and a scientifically rigorous experiment. Okay. Modern techniques help us to do some things better, but we have to understand the basics very clearly. Okay, then there's a question. What do you mean by supersaturated solid state? Okay, I've not touched this business of supersaturated condition. Okay, so we haven't done it simply because this goes into non-equilibrium thermodynamics. And that is not in the scope of this course. But we'll give an example where this issue comes in. What we said is that if we take a cylinder piston arrangement and we have a substance there which is, say, a saturated liquid, throughout this discussion we have said that as soon as we give some energy to this, at constant pressure it moves up, immediately some vapor is formed. In reality, what happens? This or its counterpart in a flow, that you are pumping in saturated liquid and you are heating it now, and you expect that vapor bubbles will be formed. What has practically been observed is that instead of exactly happening at the saturation temperature, the liquid remains the liquid for a few degrees greater than the saturation temperature. And then it changes phase. Same thing with a solid. So this could be a supersaturated liquid or supersaturated solid. So what it's telling us is that what we learned in equilibrium classical thermodynamics, in reality, there is a slight deviation from that, and this deviation could be of the order of about 2 degrees Celsius. Why it happens and how it happens, we cannot explain it from classical thermodynamics. We have to get back to both first non-equilibrium thermodynamics and then go back and look at all the aspects from statistical thermodynamics to explain this phenomenon. So we are not going to go into these parts into a beginning course in thermodynamics. Advanced courses is where you will be worried about. you.